D4, the last half of D4 is talking about buffers. So when we say buffers, these are basically chemicals or solutions that resist changes to pH when you add a strong acid or a strong base. So it's a chemical that when you add a drop of strong acid or strong base, the pH of that buffer stays relatively the same. So you have to know that buffers are made up of conjugate acids and conjugate bases. So inside that chemical, there's two molecular species. So an example used in the book is your acetic acid buffer. So acetic acid, it partially dissociates into H plus. So because this is an equilibrium expression, you can imagine that this chemical, if I add more acids to this buffer, the equilibrium will just shift to the right. Okay? And if I add a base, strong base, this base will just react with this acid to shift the equilibrium to the left. So that's how buffers can resist changes to pH, because when you put an acid, it's just going to shift to the left. When you put a base, it's just going to shift to the right. Okay, I'll measure the pH of a buffer. Okay, there's a lengthy discussion in the book. If you don't understand it, that's fine. You just need to know that the formula for the pH of a buffer is given as pKa plus log of the concentration of the conjugate base over the concentration of the conjugate acid. Okay, by the way, going back to this buffer system right here. So this is your conjugate acid, and this is your conjugate base. Okay, acid because this loses protons. So this is your conjugate acid. Okay, so this is our formula to calculate the pH of buffers. Now, there's two important calculations you need to know. Okay, so divide this into two. First is how do you calculate for pH of buffers? The problem will tell you, like you're making a buffer, for example, and then what is the pH of that buffer that you're making? Another problem that you can solve here is what is the pH of your buffer, pH of buffers after adding or a strong acid, the pH of your buffers. I'll use the example in your book on page 742. All right, so the problem there says an ammonia buffer is commonly used in biochemical experiments when high pH is required. They calculate the pH of your aqueous solution that contains 0.040 concentration of your ammonium chloride and 0.16 mole of ammonia. Okay, so just by looking at the molecular species of your buffer, so it's made up of these two species becoming NH3, right? So this is lost there. So this is my conjugate acid and this is my conjugate base. Okay, so the concentration of ammonium chloride is 0.40. We know that ammonium chloride completely dissociates into this. So if you know the concentration of ammonium chloride, you look at the molar ratio, 1:1. Concentration of this is the concentration of ammonium ion, or your conjugate acid. Okay, so let's write our formula. pKa plus log of your conjugate, sorry, conjugate base for your conjugate acid. So what is the pKa of ammonium, or ammonia? If you look at page 741 in table 1, okay? Ammonia conjugate acid is NH4 plus. I'm looking at this part of the book. This one. And ammonia, so pKa is 9.25. So 9.25 plus log of, what is the concentration of your base? 0.16 divided by 0.040. Okay, so the pH of this buffer that you're making is about 9.85. So please check that, verify that with your calculator, right? So that's the first approach, first type of problem that you need to solve for buffers. Okay, second one. This one is a little bit more challenging, so I need you to be listening very carefully. Okay, so I'm going to use the problem on page 743 of your textbooks. All right, so it says there, the hydrogen carbonate buffer was prepared by slow addition of 20 mils of 0.1 mole per dm cube of hydrochloric acid to 80 mils of 0.2 mole per dm cube of sodium hydrogen carbonate. So what is the pH of this buffer? Okay. Then the second question is, calculate the pH after you add solid sodium hydroxide to the buffer. Okay. So as you can see here in the problem, when you're making the buffer, you made it by adding a, okay, so please listen carefully. If the problem says adding a strong acid or a strong base, we will have to do the ice method. Okay. Miss, what is the ice method? So first of all, you write your equation. So the problem says you have sodium hydrogen carbonate. When you add HCl to it, it becomes this. Okay? Now, first, before you start, you have to identify which is your conjugate acid and which is your conjugate base. So obviously, this has more hydrogen than this. So this is your conjugate acid, this is your conjugate base. And then this stands for initial change in equilibrium concentration. Okay, so what is the initial amount, initial mole? Oh, because you're given volume and concentration, so you can calculate the mole. Calculate the mole. Okay, what is the initial mole of your sodium hydrogen carbonate? So this is what you're given. Sodium hydrogen carbonate is 80 ml and 0.200 mole dm cube. So concentration 0.2 times 0.080. Okay, the mole of your sodium hydrogen carbonate is 0.0160. Please verify this with your calculator. You write it here, 0.0160. What is the initial mole of your HCl? So for your HCl, you're given 20 mil and then 0.1. When you calculate that, that's 0.002. Right? Yeah, you don't know yet. Now, after they react, how much is left of sodium hydrogen carbonate? You just simply subtract 0.160 minus 0.002. 0.01. Let me try that. 0.160 minus 0.002. 0.14. 0.014. Sorry, backtrack a little bit. So, sorry there. So this is, the change will be minus 0.002, and then you put your difference here, 0.014. The change is minus 0.002. So at equilibrium, this is now 0. The change will be plus 0.002. Miss, why plus 0.002? 1 is to 1, right? So 1 mole of change here is the same as 1 mole of addition here. Okay. So at equilibrium, you have 0. Sorry, I'm thinking this is what you need. Concentration of your base at equilibrium. Concentration of your acid at equilibrium. Now we can get A plus log of the conjugate base over concentration of the conjugate.
Sorry, let me rewind. The file is
1
broken.
is to 1, right? So 1 mole of change here is the same as 1 mole of addition here. Okay. So at equilibrium, you have 0. Sorry, I'm thinking this is what you need. Concentration of your base at equilibrium. Concentration of your acid at equilibrium. Now we can get A plus log of the conjugate base over concentration of the conjugate. This is just,
Sorry, let me.
okay. Concentration equals.
The video is lagging, but anyway, so your formula now, you have the concentration of, you have the mole at equilibrium of your base, the mole of your acid. Then you just need to calculate the concentrations and then put the values here in your formula.
N over V. We're looking at this one. So the mole 0.014. Our volume, our total volume, if you look at the problem, it's 80 ml plus 20 ml. So that's 100 ml, right? So 0.1 dm cubed. Okay, so the concentration of your conjugate base divided by 0.1 is 0.14. Okay, and the concentration of your conjugate acid 0.002 divided by total volume 0.1. Okay, that's what you need to put here. So concentration of conjugate base is 0.14. Conjugate acid is 0.02. Okay, plug that in your calculator. You should get a pH of 7.21. Okay. Now it doesn't end there. There's another question. So this was the pH of your initial addition of HCl to your buffer. And then you add a base. Remember, you can add an acid or a base to the buffer. When you added the base, that's there. You added 0.02 grams of sodium hydroxide, pH. The same thing as a, okay. Now, you have them.
Sorry, excuse
base.
Lagging again. So we're adding a base.
Molar mass because you're adding a base.
Okay, you're adding a base. You're given the mass of the NaOH. So just divide it by the molar mass, then you get the mole of the base that you're adding to your buffer. Okay, so this is the mole of the base that you're adding to your buffer.
So you write your equation first. So you're adding a base. So therefore, in this buffer system, when you add a base, this will react with the base because it's the conjugate acid, it's the acid. So let's write the new equation. Okay, so this was your conjugate acid from earlier, and we know that this is the conjugate base. Okay, so we do an ice method. So the initial amount of this, not concentration, mole, 0.002. Okay, it was from here. It was from here. We're starting here because we're adding a base here. So the initial mole is 0.002. The initial mole of your base is 5 times 10 to the negative 4 mole. The initial mole of hydrogen carbonate is initial mole 0.002, 0.014. Remember, this is the mole. So this is the mole of HEO3. This is the mole of your CO2H2O, carbonic acid. So change will be.
So the mole of the conjugate acid is from the previous calculation we had. Also the mole of sodium hydrogen carbonate from the previous calculation we had.
So minus 5 times 10 to the negative 4 is going to be limiting. Minus 5 times 0.014. Remember, to the negative 4
Sorry.
of your 0.1. We need 0.0.
Okay. The file is broken again.
Divided by 0.1.
Please wait.
10 to the negative 4. This to 1, so that's going to be equal to. Assume this 0.014.
Okay. My file is broken, so let me just explain to you. So after this, so the change is, so minus 5 times 10 to the negative 4, minus 5 times 10 to the negative 4, plus 5 times 10 to the negative 4. Then you get your equilibrium moles. So 0.002 minus 5 times 10 to the negative 4. So that's 0.00150. This one is 0. Then this one is 0.014 plus 5 times 10 to the negative 4. So it should give you 0.0145. Okay, so you need 0.0145. Then you need the equilibrium mole of this 0.00150. Check the textbook, please. So that's what you have for the mole of your conjugate base, mole of your conjugate acid. So the next thing for you to calculate is the concentration of your conjugate base and your conjugate acid given their moles.
This is the mole. Is this base? Okay, as usual, before we proceed, we need to know the 0.15 conjugate base. Sorry.
So from the mole, calculate the concentration. Okay, from the mole, calculate the concentration. Once you have the concentrations, then you can put the numbers here into your equation.
Log of our 0.145 divided by 0.015. Okay, you plug that in your calculator. It should give you a pH of 7.35. Okay. When you added the base,